Hi, welcome back to Calculus. Today we're looking at section 3.4, the derivative as a rate of change. So we talked about rates of change back in chapter 2 a little bit, and now we're really going to be digging into this some more. We're going to be looking at this derivative because the derivative, since it is the slope of the curve at a point, is really the instantaneous rate of change at x sub 0. So the f prime of x sub 0 is the instantaneous rate of change at x sub 0. Importantly, we need to pay attention to the units. The units are going to describe for us what that rate of change is. And so that's going to be really important. And we'll look at that here with a couple of examples. But they will describe for us what that rate of change is. So for instance, if you're driving in your car, an instantaneous rate of change is going to be miles per hour, probably, most likely. And those units there that would be part of the problem will describe what the rate of change is for us. And so we know what miles per hour means. That's something we use all the time. But it is worth having those units in mind because they are going to help us understand what the heck this derivative is even doing. All right, so let's take a look at this first example. We're going to look at a circle. So we know the area of a circle is a is equal to pi r squared. We could write this, in fact, let's go ahead and do that. Let's write it as a function, a of r, because the area really is a function of the radius of the circle. And so what we want to ask is this: how fast does the area change with respect to the radius when the radius is 20 centimeters? So a couple of things here before we start. First of all, area is going to be centimeters squared. Okay, we know that. And excuse me, the radius is obviously in centimeters. So let's hang on to that. We'll talk about that when we get down here to the bottom where we have some strange looking units. So all I did was I took the derivative of the area with respect to the radius. Okay, no dx here because we are working with radius as our variable. And please note, pi is a constant. So all I did was drop the exponent down, and the derivative here is 2 pi r. Which is super interesting. That's also the formula for the circumference of a circle. That's interesting. What that means is that the change in the area is like adding a little bit of circumference around the outside. Anyway, so we can plug in the 20. 2 times pi times 20 is 40 pi, which works out to be 125.66. And the units then, since we have a change in area over the change in radius, and okay, that's really one way we can think about this. Change in area over the change in radius. That's going to be our average rate of change. Or I'm sorry, not average, instantaneous rate of change. And so we have our units centimeters squared per centimeter. Well, what does that even mean? Well, all it means is this. The area is going to change 125.66 square centimeters for every 1 centimeter change in the radius. Okay, right? That's what that really means. It's just this rate of change that we have here, and it's a comparison between the area, which has centimeter squared units, and the radius, which has centimeter units. So we're not going to reduce those units. You would never reduce the units here on this one. The units, the square and the regular centimeters, describe this rate of change for us. So let's go on, and we're going to look at some physics problems here next. Okay, so before we get into any actual examples, I need to run through some little bits of physics and how these relate to each other. So we first want to talk about position. S is going to be a displacement function, so it's basically how far away from a given point that you are. So you can think of it on a number line. Displacement could either be positive or negative. There are all sorts of ways to think about it. If you're dropping, say, a bowling ball off of the roof of a building, the displacement, might be a little bit weird. Your positive direction might be down because you're measuring how far it falls. But so it's a function, and it's usually a great place to start because here's what we get out of a position function. If you take its derivative, you get the instantaneous velocity. A change in position is velocity. That's what we call the speed that you're moving at, right? If you get in your car and your cruise control is set at, you're on the highway, so 70 miles per hour. Your velocity, 70 miles per hour, is also the change in your position, right? It's how far you're going from point A to point B. So velocity is equal to the derivative of s with respect to t, or just f prime of t. It's worth noting, velocity can be positive or negative. Okay, so if we think about your house as being point 0, when you leave your house, your distance is increasing, so your velocity would be positive. But when you come back, when you return home, your velocity is kind of sort of technically negative because you're returning to that starting point. All right, so velocity can be positive or negative, but we don't usually think of that. We think of speeds as being positive, and so we have a speed which is really just the absolute value of all the velocity. That way you're guaranteed that it's positive. So remember, velocity is basically speed with a direction. Are you moving away or are you coming towards? If you're moving away, it's positive. If you're coming towards something, it's negative. Let's move this way. Then we have acceleration. Acceleration is the derivative of velocity, or the second derivative of the position function. So f double prime of t. And acceleration is what pushes you back in the car. All right, so you get in your car. In order to get up to that 70 miles per hour that you want to set the cruise control at, you have to accelerate. So what you notice is when you push down, especially if you push down really hard on the gas pedal, you feel like you're getting pushed back into the seat of the car. That's due to acceleration. Once you get up to your cruising speed and you set the cruise control, you don't feel that anymore. So you're not feeling like you're being shoved into the seat the entire time you're driving, because you only feel that when you're accelerating. Once you get to your cruising speed, you're kind of there. There is no acceleration. So acceleration is what pushes you into the car. And there is a fourth one in physics. I'm not really quite sure how to describe jerk, which is actually the physics term for it. How about that? And it is the third derivative. It's the change in acceleration. So yeah, probably a lot of jerking. It probably does exactly what it says. If you're driving a car and you're driving in such a way that you feel a lot of jerk, you're probably getting thrown around in the car a fair bit. So I guess this would be, if you were to go from flooring it, so you push the gas pedal down as hard as you can, to stomping on the brake, right? You're going to change acceleration really quick. You were going from accelerating in one way to accelerating in the other direction. And so anyway, it's the third derivative. It's the least, I don't know, in my mind, it's the least useful of the bunch, but I suppose there are probably engineers and such out there who use that all the time. All right, so next we're going to do a great big example. It will probably take more than one time through the board, so just kind of hang out and I'll get another board.